All right. Good afternoon. Excuse me. Good afternoon, everyone. How you folks are doing? Great. Okay, I'm glad to hear that. It's a beautiful day, and we are starting lec not lecture 7. We are starting week 7, and it's lecture 12, if I counted correctly. So we are almost at the half semester mark. So congratulations, we've made it so far. All right, so let's get started. And first, as someone suggested on the submittee forum, and I agree with that person, I think we are spending a little bit too much time on answering questions in the chat, and it's mostly my fault because I'm getting distracted, and I'm willing to kind of answer to everything that I see going on in the chat. So let me try getting less distracted on the chat, and please ask your questions in the Q&A. Okay, so we have a great panelists as usual, and they will be more than glad to answer your questions. And panelists, if you see a very interesting question, a question that you think would be of general interest and definitely should be answered, and none of you know the answer, please just unmute yourself and interrupt me when I stop talking, and serve that question to me. Okay, so we don't want any important, any interesting questions. Just let them slide. Okay, all right. So let's start for with our agenda for today. So we are a little bit behind the schedule, but luckily not by much. So let's hope that today we finish with everything that we have to finish with chapter 2, and then maybe we have time to start our new topic, Boolean logic. So that does not mean that chapter 2 MIPS we finish today and we will never see MIPS again. So some of you might have had hopes about that, and unfortunately, that's not gonna be so. So MIPS is going to be with us for pretty much the rest of the course, but we did cover all basic instructions that we need to write meaningful MIPS code. So your next lab is practicing writing leaf and non-leaf procedures. So please make sure you practice this well, because this is definitely going to be on the next exam. Okay, so procedures, calling procedures, saving stuff on stack, passing arguments through registers, through stack if you have too many arguments. So please review all the examples that are posted in earlier lectures under lecture notes, and yeah, so that would be your lab 4, and I looked at the chat from the previous lecture, and many students were requesting extra practice problems. I will get those to you hopefully by Thursday. So they all going to be on MIPS. So treat your lab 4 as another practice problem, right? Because it will be definitely, a similar problem will definitely be on the next exam. So homework 2 grades have been released. Hopefully you have already checked them out. I haven't updated Rainbow grades, but you can access your grades on Submittee, and I will upgrade Rainbow grades hopefully tonight. If not, then tomorrow. Homework 3 submission page is open on Submittee, and if you go here, you would be able to see the state of that page. And as you can see, as of now, or as of a few minutes ago when I last updated the page, there were already 6 people. Well, one of those 6 is myself. So really 5 students submitted their homework 3 code, and all of them got full credit, 80 out of 80. That's a great result. So I wish the count just gets increasing and the average just stays the same, 80 out of 80, 100%. All right, so please make sure you submit, and hopefully you have already started your homework 3. And people who already submitted, please feel free to share how long it took you to write that homework 3. So for folks who haven't really started or barely started, they have some statistics. They have some kind of indication of how long it might take them to finish homework 3. All right. And back to my Sublime. All right, homework 2, homework 3, exam 3. Grading is in progress. It is going pretty slowly. I have to admit, it's a hard exam, not only to take, it's also a hard exam to grade. So please be understanding. Our TAs and mentors are doing everything they can. And problem 6. So yeah, we will go over our past polls, and problem 6 was clearly the champion in one of the polls that was asking for the hardest problem. Okay, so the vast majority of students voted that problem 6 was the hardest, and we decided to convert it to extra credit. So that means that problem 6 was 20 points. So that means if you solved problems 1 through 5 and got 80 on those problems, that is equivalent to full credit on the exam. And whatever you earned on problem 6 would be extra. It will be added to your grade, so you can go over 100 on this exam. Okay, and there's no cap. So if you did anything on problem 6, then of course this extra credit will help you make up for points you might have lost on other problems. And if you did well on all other problems, then you can actually go over 100 on this exam, and that extra credit would apply to any other exam grade. So if you lost anything on any of the previous exams, then the extra credit from this exam you will be able to use it to repay that. Okay, so hopefully that's good news. This is something that many students were asking for, and I think extra credit is a good decision in this case because it is fairly easy for us to implement, and it's not just like dropping problem 6 because we want to be fair to students who invested their time in problem 6. We want those students to be rewarded with something. And so I thought, someone suggested less lecture. Someone suggested let's do it extra credit. So I thought that was, that was a fair and balanced solution to this. Okay, so and now we just need to finish with our chapter 2 material, and there's some additional material on x86 assembly language, and I will talk about that as well. Okay. And let me switch to my slides. All right. And first, before we have just a few miscellaneous topics to wrap up chapter 2, and this is one of them, and it's kind of a long shot because it mostly refers to the material that we will look into deeper closer to the end of this course. But this is material about parallel programming, parallel execution. So the case when we have more than one processor or more than one core, and they execute some code. Each of them executes some code, and that code may actually access shared memory. So among the architectures of different computing systems, there is like this big division. So there are systems with shared memory, and there are systems with distributed memory. So basically what it means is, in a system with shared memory, there are multiple processors, but there is a single memory. So all programs share the memory, and they can use this shared memory as a way of inter-process communication so that they can exchange data. So one process writes something to some variable, some area of memory, and the other process would be able to read that value in. And So that, of course, is very convenient on one hand, but on the other hand, it raises a few problems. And one of them is known as a data race. And that means that, well, some operations of updating memory or writing to memory, they are not what we call atomic. That means that a process may be interrupted as it was updating their memory, as it was in the process of updating memory. So imagine just something as simple as an increment. You think, what can be easier than an increment? You think of it as an atomic operation that either executes as a whole or does not execute at all, right? So it turns out that even an increment is not by itself is not an atomic operation, because if you think about it, to increment, you have to read the current value, then perform arithmetic operation, addition, and then you have to store the new value back into memory. So it's at least 3 operations, not one. And what happens if a process gets interrupted while it is performing this increment in the middle of in the middle of this process? Of course, then it means that the value has been partially computed, but let's say not written back to memory. And then when this process resumes, it might continue from where it left off, overwriting the value in the memory that was in the meantime written to that shared memory by some other process. Okay, so this is the result of increment being non-atomic, and this is known as a data race. Why is it called a race? Because you can imagine like different processors racing to see which one of them would be able to write their update to the memory first. All right, this is a shared memory system. Okay, and just to give you a very brief conceptual description of a system with a distributed memory, that's when each processor has its separate memory. So on one hand, it's a lot easier to handle by each individual processor because this memory is not shared, so it belongs to a single processor, so there are no races. The data races do not exist. On the other hand, the problem of communicating between processes is harder because they cannot exchange data through the shared memory. There is no shared memory. And then some other mechanisms have to be introduced that would allow processes to share data, for example, by sending messages. Right? So that's a very common method. All right, so that's a brief overview: shared memory systems versus distributed memory systems. And if we are in this paradigm now of shared memory systems, then we have multiple processes sharing memory, and we have this data race when P1 writes and then P2 reads. If P1 and P2 are not synchronized, then the data may be in an invalid state. All right, so the result of the operations that P1 and P2 perform depends on the exact timing of P1 and P2, exactly how and when they were executing their instructions in the order of accesses, where access is memory access operation, either a read or a write. So synchronization in the general sense means that two processes are aware of each other and kind of look at each other as they are progressing through the instructions. Okay, so for example, if one process reaches a certain point in code and it notes that it is ahead of P2, it may need to wait for P2 to catch up. Okay, so that is known as a barrier. So sometimes we want processes to wait until other processes finish a certain part of their code. So that is one of the examples of synchronization. So that synchronization, and it's important to understand that it only plays a role when we have multiple processes, when we have some kind of parallel processing, right? If it's a single process, a single processor, that there's no synchronization required. However, even with a single processor, we might have multiple processes. Imagine that you're running your operating system like Windows or Linux, any of the modern operating systems, on just a processor that has, it's a single processor with just a single core. It's a single processor, but it's multiple processes, so all synchronization discussions that we are currently having, they still apply, because it's still a competition. We have multiple processes that may share data, and that may change the same areas of memory. So to deal with it, we typically need hardware support, because to implement the atomicity, that feature that we mentioned was causing the data races when, let's say, we thought our increment is atomic operation, but it's not, and we want it to be atomic. We want it to either execute as a whole without being interrupted in the middle, or not even start executing at all. So that kind of requirement calls for hardware support, and that support is usually built in all the modern processors. So that kind of support allows us to perform atomic read writes from memory, and make sure that no other process accesses the location that we are reading or updating in memory by the other processes, right? So if one processor reads or writes a certain memory location, then no other processor is allowed to, to interject, would not be allowed to read and write the same location. Of course, updating or reading or writing another location would be perfectly fine. So it could be a single instruction. That hardware support, of course, is reflected in their ISA, instruction set architecture, but it may not be. So it depends on the ISA, it depends on the architecture. So a typical example would be an atomic swap operation, right? So we talked about increment. That's one example of an operation that we would like to be atomic. Another example is a swap between a register and memory. So if you think about MIPS, we so far we haven't had a way to ensure that such a swap would be atomic, because we cannot do this with a single instruction. Okay, so a single instruction would be atomic, but it's not a single instruction in MIPS, right? You have to load value from memory into register, and then store the value from the register into the memory to perform this swap. You cannot do this with one instruction. So that means that in MIPS architecture that we reviewed, an atomic swap would have to be more than one instruction. But that by itself is not sufficient. We have to have some hardware support that ensures that between those instructions, the memory location that we are loading from has not changed. So we have to have some additional instructions for that. And this is exactly what happens. So here's an example. We have additional instructions. We need a pair of them. One is called LL, load linked. Another one is called SC, store conditional. So load linked loads from the memory location into the register. So here's the format. And as you can see, it's similar to LW, load word, but it has the additional feature that it puts a watch on this memory location. What is that memory location? The address of that memory location is computed as follows. The base address is in register this RS, whatever the register in the parentheses, and then the offset is added to this base address. This gives us the address of the location in memory that we want to load from. And then the second instruction is store conditional. So it stores the result in memory. The result is coming from a register. So it's like SW, similar to SW. You see the format is very similar. It stores the value of the register RT into the memory location given by their effective address, where the effective address is computed as their value in RS plus offset. But it has an additional condition. That's why it's called conditional. It would only succeed if their location, this offset, this RS plus offset, has not changed since the LL instruction. Can the offset be registered? No. It has to be a literal. It has to be, because essentially it's an immediate value, right? Recall our previous conversation about the formats of instructions, and you will see that LW and SW, they encode this offset as an immediate value, so it has to be an immediate value. If you need it to be a register, then there's a very easy solution. Compute their effective address yourself by adding your two registers, one with their base address, one with their offset. Put it in some register, use that register as RS in parentheses, and just set offset to 0. That's very common. That's very commonly done. All right, so this SC store conditional succeeds if location has not changed since LL was executed, and if it succeeds, if SC succeeds, it puts 1 in RT. So it does modify RT, which is, not something SW would do, right? So it's an additional thing that SC does, and it's crucial because we want to know whether our store was successful or not, whether the location that LL was reading was actually modified or not, since in between LL and SC. Remember, these two instructions are separate instructions. They can be interrupted. We cannot prevent this unless we introduce an additional single instruction that kind of combines the features of both LL and SC. There's no way we can ensure atomicity, but without doing any extra work. But with two instructions, we can at least see if LL has changed, and if so, we can just try to repeat the thing, right? So we cannot prevent someone from changing our memory location in between LL and SC, but we can structure our code so that if that happens, we repeat the process. We do not stop here. So the end result would be equivalent to an atomic swap. So if the location has changed between LL and SC, then we return 0 in RT. Then SC writes 0 in RT. So this is their piece of code. So you see that it is somewhat conceptually similar to a loop. So here we are trying to swap the value in S4 with the memory location whose address is in S1. So first we want to copy S4 from the register S4 to T0, because then we will be storing from T0 to the memory location. And then we have our pair of instructions, LL and SC. So LL computes the effective memory address based on the value of S1 and 0, and loads that value into T1, okay? So this, from the memory, it goes into T1, we loaded it, and then we want to store from T0 into the same memory location. And remember, T0 was loaded into T0 was loaded with a value from S4, right? Because it's a swap. It's a swap between S4 and memory pointed to by S1. Okay, so, and now if indeed no other process changed our memory location pointed to by S1 between LL and SC, then SC was successful. It means it did write the value of T0 into their memory pointed to by S1, and in addition, 1 was put in T0. So now if we compare T0 and 0 register, which has 0, they're not equal, and we do not take this branch, which means that we just continue to the following instruction, and we put T4 into T1 into S4, so we complete our swap. If, however, there was some other process that interrupted, and in between LL and SC, it was able to modify the same memory location pointed to by S1. Then SC would be able to detect it, and it would not perform the store. It would not modify this memory location, and it would put a 0 into T0. And then we analyze with BQ, we analyze T0. Now it is equal to to 0, and we just go to try. So we keep running in this loop until our swap is successful. Okay, yeah, so it is the same memory location, exactly. So that ensures that two processors are synchronized. So how do you know why is it a form of synchronization? So I like to draw timing diagrams using vertical axis, okay, like that. So suppose this is processor 1, suppose this is processor 2, okay? And so this is a time, so time in whatever units, seconds, or whatever, time goes down, so time increases in the downward direction. And so let's say P1 is executing LL here and executing SC here, okay? So, and so this is time, so of course everything takes a certain amount of time. So imagine that P2 here has a store word for the same address, okay? So that means that P1, the swap that it is performing would not be successful because P2 in between LL and SC was able to change their location pointed to by S1. And therefore, SC would write 0 to T0, and then this BQ would send us back to try. Okay, so we would then execute after this SC, we would execute BEQ, and then we would execute add, and then we would execute LL, and then we would execute SC again. And now imagine that P2 was not making any updates, and therefore it was successful. So we would have BQ here and then add here. Okay. So you see how P1 was actually delayed because it had to ensure that the swap is atomic. Okay, so that means that now P1 and P2 are not completely independent because P1 cannot just proceed under the impression that it is the only process and it can just proceed at full speed because it now sees the effects of other processes. All right, so here's this process 2, and P1 had to kind of do an extra loop in this atomic swap because of something that P2 did. So you see, that is a form of synchronization. Okay. An atomic swap is a swap that is executed as a whole or not executed at all. So it cannot execute partially, and partially would mean that the value of the swap is changed in the middle of the swap. So, imagine the memory. So the memory, and let me draw another picture. So we have two registers involved in this, S4 and S1 has the address. So S1 is actually like a pointer. We don't care what the value in S1 in, but it points to a location in memory. Okay, and we have in S4, this is a real value. So let's say, I don't know, it doesn't matter, 10, and in memory we have value 20. So we want to swap them. and that swap has to make sure that the values are, that the end values. So let me. So that the new value in S4 is 20, and the new value in memory is 10. Okay, so that's what we want to happen. Okay, and the only way to ensure that this happens is to make sure that the swap is atomic, because if it is not, let's see what could happen. Let's imagine that we just had a pair of instructions that would be load word and then store word. Without atomicity, some other process could have jumped in and store word, form store word. Store word in between. So what then would happen is our first process, P1 in this diagram, reads 20, but then some other process writes 15. So we put this 20 here because that's what we read. And then we store 10 here because that's what we have, overwriting this 15. So that is a problem, because then the result of the other process, the value 15 that the other process put in the memory, is effectively erased. It's like it never existed. And we don't want this to happen. And a very easy example would be, imagine that you are processing bank accounts and you're using multiple processes. So imagine one process starts with the balance of 100, and it needs to process plus 10. And so $100 initial balance and a deposit of $10. And the other process starts, it starts with the same balance, and it processes a withdrawal of 20. Okay, so the net result should be $90, right? So 100 plus 10 minus 20. But if these are two processes not properly synchronized with each other and not ensuring the atomicity of processing the deposits and withdrawals, then we would have, let's say in our scenario, their memory would contain 110, right? Because the P1 would read 100, add 10, 110, it would overwrite 110, despite the fact that maybe in between P2 performed its own modification of the variable. Okay, so we will lose whatever processing was done by P2, and of course that would lead to our balances not being balanced. So our balances would not match their sum of transaction amounts. Okay, so that's a big problem. That's why we have to be careful with parallel processing. Parallel programming is hard. It's a lot of fun. I think it's a very rewarding activity, but it it is fun. You have to solve. You have to think in 4 dimensions. You have to think about the time dimension in particular and how things are synchronized. All right. So that was that, and we will talk more about it later on when we talk about specifically parallel programming. This was just one example that hardware support, a support from their, from the part of ISA is required to ensure synchronization and atomicity. All right, translation and startup. Most of this stuff we already talked about, but let's just wrap up. And so with translation, when we are writing our code in a high-level language like C, it has to go through the compiler, and the compiler might generate an assembly language program. It doesn't have to, but in many cases it actually does. And if you're using GCC, you can actually supply a flag that would show you their assembly language or the internal language that your high-level C code is translated to. It would have an S extension. It would not be the a machine-dependent x86 program. It would be rather an assembly language that is specific to the C compiler, so it would be the internal language of the compiler, but it would be close. So we can just ignore those minor differences. Okay, so that is that assembly language or machine independent language module is actually binary, so it can be represented with just codes, with just numbers, and as we have seen with MIPS, and that's why it's called an object module. So please know this term may be misleading for you, may sound misleading for you, because this object has nothing to do with object oriented, right? So the term object module predates object oriented paradigm by a few decades. So it's object because it is binary. It's no longer a text. Okay, and then of course we might be using different libraries. We might be using we might be structuring our code so that it contains in more than one compilation unit. So all these pieces have to be combined together through a linker. Okay. So, and we talked about it even with GCC. We saw how you can compile things differently, how you can compile things independently if you have more than one source code, and then just link them together. And we also played with linking the math library. And so when we link it actually creates a single executable file that can be then loaded directly by the operating system in the memory, and then it will be executed. So this process is called static linking because we are linking everything that your code might potentially need into a single executable file. And if if a particular library is needed by multiple programs, it will have to be physically included in every executable where it is needed. So that seems like a little bit not so effective, because imagine SQRT is used, let's say, in 90% of your programs. And I'm making stuff up. Maybe, of course, maybe it's not 90% of all programs, but think about some common library procedure, some common library routine that would have to be copied in every executable file that uses it. Okay, so that seems to be not very prudent. So it's a simple process. Static linking is simple. That's its major benefit, but it's not the most efficient. Can we think of a more efficient way of doing things? Sure, we can say, well, can't our executable find the correct library function dynamically at runtime so that we only need to load that library once in the memory, and then all programs who need that function, procedure, whatever, like sqrt, they just link to that single copy that exists in memory. And such method, of course, exists, and it's called dynamic linking. So in in Unix world, it is known as SO, shared objects. In Windows world, it is known as DLLs. I'm sure you've heard this abbreviation, DLL, dynamically linked libraries. All right, so pseudo instructions. This is something that we've dealt with. We've seen them. So those, yeah, and I like how our textbook calls those pseudo instructions figments of the assembler's imagination. Right? I didn't know assemblers have their own imagination, but apparently they do, according to our textbook. So anyhow, those pseudo instructions are not real instructions. They are what is known as syntactic sugar. Why is it called syntactic sugar? Why is it syntactic? Because it's just a piece of syntax, right? There is no real deep meaning behind that. Why is it called sugar? Because it's something that is, well, not good for you in a sense, right? So it's something that you don't really need that much. Well, I'm kidding. Of course, we all need some sugar, but syntactic sugar is something that you can easily do without. It's called sugar because there's a direct correspondence between this syntactic sugar feature, like a pseudo instruction, and a real instruction. Okay, so we know that we cannot move from one register to another for one, because it's really not move. It should have been called copy, right? Because in our common language, common intuition, moving means that the stuff that you move is no longer in the place where it originally was, whereas the semantics of this instruction is really take the value of t1 and write it to t0, but the value in t1 stays, right? It's not erased, it's not like eliminated. So essentially it is closer to copying than it is to moving. But in any case, we see that introducing such an instruction into our MIPS ISA would be unnecessary, because we can do the exact same thing with the existing instructions. So if we do add the value of their source with the 0, and then so we are adding them, and then we place them into the destination to 0. That's exactly what we want from this copy move instruction. Okay, so we don't really need this instruction. For a human, it might be convenient to type move and avoid typing their $0 explicitly, but that's why such a pseudo instruction exists. But it doesn't really add any expressive power to our ISA, to the set of instructions that we have. We want to keep the set of instructions minimal. We only want the instructions that add something meaningful, that adds some semantic power to our instruction set. We don't want to include stuff that is really unnecessary. So those are instructions that's why they're called pseudo instructions. And BLT branch on less than is another example. And there was a question on the Submittee forum that I answered this morning about sub and add I and sub I. So you can do sub with an immediate value. You can do add with an immediate value. But again, this is just a syntactic sugar. And as I explained in my answer in that thread, it just translates into the regular add I instruction. And with sub, it's even worse. It actually gets translated into two instructions, where if you use add I, you could have done this with a single instruction. And that's why, yeah, so I know there's a starter code that we provided to you in the homework 3, that uses sub with an immediate value. It works, but if you want to really shine your MIPS knowledge, you would probably try to avoid pseudo instructions. And move is a common one, but sub with an immediate value is not that common. All right, and so since some pseudo instructions need multiple real instructions to implement what they do, they often use those instructions use this assembly temporary AT assembler temporary register to store intermediate result between the instructions. Okay, so as this code with BLT shows, right? So AT is written to in here, and AT is used for the to calculate the condition. All right. So now back to producing, to the whole compilation linking process. So to produce an object module, the assembler translates the program into the machine code, and then there's a number of additional pieces of information that we need before we can actually produce the final executable, right? Binary executable. Remember, it is called ELF in Unix world. It's the most common executable file standard in Windows world. It is exe executable, right? Exe, and there's an older standard called com for command files. So there used to be two formats for executable files in Windows, and they are all different. So there's no compatibility between operating systems at the level of the binary code, right? That's why if when you want to install your favorite software, you have to either compile it from sources or you have to download a binary version for your specific operating system. If you just take an executable file from Windows and copy it to Linux, it's not gonna work, and vice versa. All right, so this executable file has a very complicated structure. Well, COM files in Windows, early Windows and DOS system were very easy, but exe is more complicated, and ELF is more complicated. So they have a header that describes the contents of their object module. They have the segments that correspond to text or code, and static data segment, so statically allocated data, and symbol table, so that lists all global definitions, like all their functions and procedures. And if you compiled with a special flag like -G in GCC, it would include debug info, and it also has the relocation info that shows where each piece of compiled code can be moved, and how different pieces are linked to each other. So it's pretty complicated. Okay, and so to link an object module, we need to invoke a linker, supply it with all the object modules that we want to bring together as a single executable, and the linker will merge the segments. So it will look at their object code from each of the object modules and kind of combine them together, resolve labels. So for example, determine the addresses of every label, and then produce an executable that would be capable of running directly by the operating system. Okay, so an image is just because this file is loaded, this executable file is loaded directly as is by the operating system. So it's like a snapshot of the program with all the parts that are needed to execute that program in a single executable file. And remember, linking may fail. Remember how we were struggling with a math library if you forget -lm flag? Compilation works, but linking fails because there's no SQRT or whatever math function you were using. So the linker, if it's not able to find it, it will fail to produce an executable file for you. All right. So with virtual memory, things get a little bit more complicated, but actually there's a benefit to using virtual memory because now each process has its own virtual memory address space that it may assume belongs exclusively to that process. Okay, so that's why we can leave certain location dependencies to be fixed by a loader that loads that executable image rather than having to absolutely resolve all such dependencies at their linking stage. All right, so how do we load a program? So we basically read the header of the executable file, like that ELF header or the exe file header, and that determines the sizes of all their segments, like data segment, text code segment. Then their loader, which is part of the operating system, by the way, creates the virtual address space and copies text code into the corresponding segment, data from their statically allocated data segment into memory, and so forth. Then it sets up argument on the stack, initializes the corresponding registers at the hardware level, like all those stack pointer, frame pointer, general global pointer, or general pointer GP that we talked about when we were discussing MIPS. And remember, GP is in the middle of their static data segment. And then just jump to the startup routine, right? So like your main method. Yeah, that's it. When the main method or main procedure exits, then it just does a syscall with v0 of 10, right? So remember, so syscall, we can actually exit the program with a syscall. Okay, and here there are slight differences that I explained before between different simulators. So Mars expects you to call syscall 10, whereas in QtSpim you can just return from the main as if it were a regular procedure. So you just do JR with $RA, and that's how you end your main, because there's an additional code that QtSpim actually executes that acts as a miniature operating system. Okay, and so now the fun part, the hard part, dynamic linking. Okay, so when we only want to have one copy shared by all of the library or some other object code that we want to be shared by all programs that need it, then we go with a dynamic linking. So it requires that that library procedure code is relocatable so that we can move it around in their memory if needed, and it avoids this bloating that we discussed a few slides ago, that is characteristic of static linking when we have to physically include a copy of their library code into every program that needs it. Okay, so we can just replace this with a link to this library at runtime, and that's why it's called dynamic linking. And an additional benefit, side effect of this, is that it will automatically pick up new library versions. So you only have to update their library on your machine once, and then all the programs that reference that library will see this new version because it will be loaded dynamically. Whereas in case of static linking, you include a copy of the library function or procedure in your code, and of course it's not going to update if the library changes, so you would have to recompile or at least relink your program so that it is now statically linked with the newest version of the library. So there's this maintenance side effect that is very desirable, and dynamic linking is very common, so it is widely used. All right, and so here is the a brief description of how this looks. So we have our code, right, text code segment here, and it uses some data. So you see that there are some dependencies on the data segment, and there are also dependencies on other pieces of code, so libraries. So we have this idea that instead of statically linking, we can have a table that contains the name of the feature of the function that we need and where it is actually located. So instead of actually calling a function, we would call a stub, which contains the ID of the function, like the, let's say ID of sqrt would be, I don't know, 55, and then would have the J instruction that actually jumps to the linker loader. All right, so here is this link, right? We jump to this, and of course, jump with their with their with the label is basically a direct jump, so it has to refer to the code. And here in the link loader code, we have a remapping, so we have another jump, another level of indirection that actually shows the real location of that function, from the dynamically loaded library, dynamically linked library. Okay, so. And it's a long process, as you can see, because it has to go through several levels of redirection. And is linking how we do jump functions. Well, jumps can be used for many different purposes, right? Sometimes you just need to jump to another piece of code, but jumps are used in this mechanism that allows us to introduce an additional level of redirection. This level of redirection, okay, and thus implement dynamic linking. That is, we no longer have to store that library as part of our own text code segment. You see, that library is no longer here, right? It is actually here, okay? And we have this additional level of redirection that allows us to only have one copy in their in their system overall that is shared by all the programs, because there might be another program, right, that needs the same DLL, the same function, and it would be linked to the same thing from from a different program. Right, so this process, as you can see, is kind of long, but luckily we can optimize here a little, and we only have to do this long loading on the first call to their function, and all subsequent calls are easy because we already know where this DLL is located. We already determined this this address. All right, this is the return address, right? That allows us to return to the caller, but this address would already be determined, so we can skip this whole thing that we had to go through the first time around of determining where their library is currently located, or if it's not loaded, it would have to be loaded. Okay. All right, and Java is another language that some of you might be already familiar with. Some of you would learn Java or learn more of Java when you take Principles of Software, PSoft. Yeah, it's a programming language. So conceptually, it is somewhat similar to C++ in the way it is compiled. So it is first compiled into their executable code. All right, and then that executable code needs to be run. But the difference is, and a very important difference, is that the executable code that a Java program compiles into is not really a machine code, is not their is not their instructions of any particular architecture. It's actually instructions of some virtual processor, and that's why this code is called intermediate code, or in terms of in case of Java, a more common term is bytecodes. So those object files cannot be directly executed. We need another piece of software called Java Virtual Machine, JVM, that would execute, interpret those virtual machine instructions and interpret them by turning them into the real machine language on which the JVM is running. So this is just-in-time compiler is actually part of the JVM of the Java runtime. So this JIT, just-in-time compiler, interprets bytecodes and emits native instructions that correspond to the processor on which our program is currently running. Right? So that's how, that's a so-called virtual machine concept, and it is so if you think about C# and the .NET framework in general, they use the exact same paradigm, and it's actually not new. So the first virtual machine for a high-level programming language was introduced by Nicholas Wirth, a Dutch computer scientist who invented high-level language Pascal. So some of you might have heard about Pascal. Okay, so and C# is exactly the same. C# conceptually is very similar to Java. It's, of course, they're different languages. So C# is I think a little more complicated than as far as syntax is concerned than Java, but conceptually they are very, very similar. All right, and so let's bring this all together with this C-sort example. So here we have, a sorting problem that we need to write in C. So as I mentioned earlier, if you're asked to, and we need to implement it in MIPS, of course, and as I mentioned earlier, if we ask you to do something in MIPS and you don't even know where to start, try writing C code and then just translate it into MIPS, right? So it is important that first you need to have the algorithm in place, and then if you have no clue what the algorithm looks like, you probably won't be able to write your MIPS code. So you have to have a good idea of how the algorithm would work. And another very important idea, I think, that would make life a lot easier for many of you, would be simplifying the problem so that, if you solve a simpler problem first, then hopefully later you can, complicate this problem. You can reintroduce the pieces that you ignored, and it would, taking small steps is always easier, in my opinion. Like imagine, you are asked to perform, a conversion from, and this is your problem 6 on the exam, right? So you're asked to convert from the binary representation of 2's complement of a number in 2's complementation into their hexadecimal, and you're given those hexadecimal digits. Okay, so like I would just initially forget about doing the conversion. I would just try, can I print an arbitrary hexadecimal number? So can I print cafe babe with my hexadecimal digits, just by itself, just as cafe babe. All right, because that would allow you to write the code that would go through that array of strings, each of which corresponds to a hexadecimal digit, and make sure that you're doing all your indices correctly and you're handling that array correctly, and that kind of stuff. Yes, it's not the problem that was asked of you originally, but that would be a good first step. And then once this is done, then I would ask myself, all right, can I actually do that? I take the 4 least significant bits of my number and I print not just cafe babe, but I print cafe babe, and then the last digit would be the real digit that corresponds to the 4 least significant bits of my number, right? So I don't want to do everything at once, the entire number. I want to do piece by piece. Can I do just one digit? If I can get one digit done, then hopefully then I would be able to say, oh, okay, if I did one digit, then I just need to set up a loop that would go through all 8 digits of this number. And hopefully it's easier once you do the first digit without a loop and then add loop later, rather than trying to write the whole monstrous program at once. And it with proper techniques, it should, as I mentioned, it wouldn't be monstrous, right? It wouldn't be tens or hundreds of lines. So the entire solution would probably be like 25, 30, maybe 35 lines. Of course, if you don't do loops, then it's going to look awful, right? Then you would probably have to write a lot of code. But that just means that you're not approaching this problem correctly, right? You have to use loops. And it's the same with C, right? Imagine writing your matrix multiplication without using loops, right? You'd probably die before you get this thing to work. Okay, so that brings me to our first poll for today, and yeah, hopefully it makes sense to you. Hopefully you get, with this first poll, you get the idea that I tried to convey. It's a little funny, so take it with with your best sense of humor. All right, can you see the first poll? Yes, I will show. Yeah, I will show their old polls in the end. Hopefully, we have time. Okay. All right. So, yeah, eating elephants. I know it might not be politically correct. Who knows? But hopefully, you get the idea. Right? Do not attempt to eat the whole elephant at once, especially on the exam. Small bites, please. And then it actually you increase your chances of getting plenty of partial credit, right? If you have at least one half working correctly, maybe it's a simpler problem. Maybe it's not exactly the problem that we asked. It's a simpler problem, but you got it done correctly and it works. You're gonna get more partial credit than if you wrote the whole, this monstrous program that attempts to do the whole problem, but it fails to run and it's like completely obscure and it's not clear what you even meant by this. Okay. So we are back to our C-sort example. So we will, as part of sorting, we will need to swap elements. So we need a swap procedure. And this swap procedure is, remember, it would be called leave because it by itself does not call any other procedures. And we just need to make those decisions how we pass arguments and the return value to and from this procedure. So this is this piece. All right, we need to document this, and then this is our swap, right? So let's very quickly go over this, and we have. So we compute their index, and then we load the value using that computed index, right, from memory. So this is exactly what someone was asking earlier today, right? We want to first compute their effective address ourselves, and we do it with this add, okay? So that because we cannot use registers to denote the offset. Okay, so then we read, we load the value from one element, then we load the value from the second element, and then we store them back, just swapping them effectively, right? Whatever was read from the second element, we would put in the location that corresponds to the first element into VK and vice versa. Okay. All right. So that's the swap. Note that it does not use any S registers, and that's why it does not need to save them. But think about what if swap did use S registers? What additional? So imagine that instead of T0, for some reasons, the programmer who wrote swap were using S0. What would that, what the implication would be? Okay, what would have to be added to this code? All right, and it's clearly leave because there are no other JAL instructions anywhere in the swap. And now their main sorting procedure, it's non-leave because it does call swap, right? So it has a call from sort to swap. That's why sort is a non-leave. And again, recall what this entails. All right, so we have to make their assumptions. We have to make the decisions about how we pass in their arguments and the return value. Well, the return value is none, it's void, so it's easy, but we also need to designate their variables for indices and such, and local variables. And here is the code. Okay, so this is the procedure body for sort. So again, very briefly, hopefully it's more or less straightforward. So we have to have nested loops, one and another one, right? So that's why we have for first test, for the second test, right? So those are conditions. And so other than that, it's pretty much a straightforward translation of our C code whenever we need to swap. So we call our swap procedure. Here it is. Okay. And note one thing is, so imagine if T0 is used here. Okay. And imagine that, so T0 is modified by swap. What would that entail? Okay, that's another important problem. And if you do not follow, if you not remember those rules, if you do not follow the conventions, you might get very hard to debug errors in your code, right? Because in this case, you can see that we set T0 and then we do something based on T0. So T0 is important here. And then, we either go to exit 2 or not. And then we prepare arguments for our call to swap in A0, A1, and we call swap. So if swap changes to 0, then when we return from swap and we continue execution here, we will see the value of T0 that was set by swap. And that can be undesirable. That can be dangerous. That can be not good. Is it good or not in this case? Well, we can see. Do we use T0 here? No. And then we jump for to test, and here we overwrite T0. Okay, so in this case, even if swap changes to 0, it's not dangerous for our sort procedure. So we don't have to save T0. But if we here, after we returned from swap, we were doing something with T0, assuming that the value didn't change. So for example, imagine here we had something, and of course it's not needed for this algorithm, but just for the sake of argument, yeah, let's do add I1. Okay, so if we had 1 plus T0 here after we returned from swap, assuming that it's the same T0 that we wrote here or that we set here, then our code would get broken because swap changed T0. It's no longer what we set it to here. And this means that the logic of our program is broken. So that means that we either have to use a different register that is not changed by swap, or here before calling swap, we would have to save T0 in the stack or on the stack. Okay, is that making sense? All right, and here is the whole thing all together. Note how our sort procedure saves all S's and RA, of course, right? It has to save RA because it is a non-leaf, and it has to save all S's that it uses because there's main. So when we return from sort and we go back to main, main should not see any of the S registers change. All right, and here is the second pop quiz for today. Just two for today, but we had a few lectures when we had a lot more, and yeah, some people are still earning their lay days. I think some people have over 95% of those sub-mini polls done and done correctly. So that's pretty impressive. Please keep it up, folks. It's really a pleasure to see very high participation rates from some students. All right, and now let's talk a little bit about performance optimization and just wrap up with our chapter 2, and we will talk about x86 assembly very briefly. I will point you to additional slides that you are welcome to look at if you have spare time, but in the overall scheme of things, we don't have enough time to go into x86 assembly into more depth. Maybe if there is demand, if students want to, I can go over additional material, but for now I'd say let's just kind of keep it low key. All right. Anyhow, the compiler optimization is very important because there are flags that you use with a compiler. So hopefully you have seen those flags with GCC and G++, right? So this is O, this is not 0, this is O, and like if you run the real compiler, you would just do a dash, right? So this is the optimization level. So O stands for optimization, and it's just the aggressiveness of the optimization. And so why do we have different flags? Why not just use the most aggressive optimization? Well, it turns out that some code, in particular parallel code, might not work if you optimize too aggressively, because aggressive optimization, like with their -03 flag, may be making certain assumptions that are not true for code that executes parallel, like if you're writing multi-threaded code using POSIX threads. Okay, so that's why we can vary the degree of optimization, the aggressiveness of the optimization. And if you read the documentation, it will tell you exactly which optimizations are allowed by each of those flags, from none, no optimizations, to 0, 1, 0, 01, 02, 03. All right, so we can see the relative performance, and so this is specific for this piece of code, right? So of course your mileage may vary. It will vary depending on the code, and you can see that yeah, optimization flags do increase performance. So with none, we take it as 100%, and with optimization flags, it's better. It's more performance by a factor of close to 2.5. And as you can see, and it's very hard to see on this diagram, but the optimization with O1 is slightly less than with O3. So O3, you can see it gives you slightly higher performance, not by much, but still. All right, what do we have to pay for optimization? Well, of course, if there are no optimization, then the instruction count tends to be the largest, and then when we do optimize, you see that the instruction count drops dramatically, but then as we are getting into more aggressive optimization, the instruction count increases. It is also important to understand that there are different criteria for optimization. What do you optimize for? Do you optimize for their executable code size? So you want to have their smallest executable file. Do you optimize for speed? Right, there might be different degrees of optimization, and so those different flags, O1, O2, O3, they are a blend of different optimizations. So you have to look at exactly the blend that you need. And clock cycles, quite predictably, no optimization. It's the highest, and that's why the performance is lowest, right? Because we have to do the highest number of clocks, and then with optimizations, you see that their clock cycles are much lower. Okay, and amazingly, like CPI, if you look at clocks per instruction, then O1 optimization has the highest, right? And of course, we want to have the lowest CPI in general, right? And this is something that O3 delivers, right? Because we have all other things being equal, we want CPI to be as little as possible. So, and now you can compare instruction count and CPI, right? Remember, we talked about it in their homework and in their exam. So we need to look at both instruction count and CPI. So yes, CPI for O3 is quite significantly lower than for O1 and O2, but the instruction count is also higher. So it kind of mostly balances each other out, right? We have smaller clocks per instruction, but we have more instructions. So if we multiply, we as you can see, we still get a benefit as compared to O2, but this benefit is not that huge, right? All right, so of course their effective language and algorithm is significant, right? So this is the comparison of C code for sorting. It's the same example, sorting with different optimization flags, O1, O2, O3, and Java code with integers, and Java with JIT optimizations. So JIT as the interpreter on the fly. So JIT stands for just in time. So it basically is an interpreter with advanced features that allows to kind of partially compile on the fly. And so it is roughly equivalent to using optimization flags with their C compiler. So we can see the performance, of course, with JIT is higher than with just pure interpretation, right? Pure interpretation, of course, is very slow. And earlier versions of Java were using interpretation, and of course it was abysmal, and unfortunately it damaged Java reputation so much that even to this day many people think that, oh, Java is so slow. It is not nearly as slow as it used to be, and actually it can be faster than native code in some cases. All right, so lessons learned. Both instruction count and CPI are important, but they are important together, not in isolation. And it's important to use compiler optimizations for the production version of our code. Of course, if it's a developer code or even something you submit on Submittee, we compile the code with little or no optimizations usually, but we compile all students' code with the same flags, so it's a level playing field. But if you are delivering a code to their customers, then of course you want their you want it with the highest optimizations, provided that your code still works correctly. Like I said, aggressive optimization can actually highlight some of the bugs that were not manifesting themselves under not so aggressive optimization. And Java code is interpreted on the fly using this JIT just-in-time compiler, and it is significantly faster than JVM interpreted. Truth be told, even with JIT compilation, in many cases, Java is slower than native code, where native code is something that you get like out of your C or C++ compiler, because it's the code that is instructions specifically for that architecture, like x86 architecture, whereas the code that you get from the Java compiler is universal. And you might have heard one of the Java's mottos, write once, run everywhere. So it's kind of hinting that you don't have to recompile your code for every platform. You just compile it once. You write your code once and you run it everywhere. And of course, people who are into Java, sometimes jokingly say, write once, debug everywhere, because this idea that we just compile once and then it will automatically run on all the other systems, it works, but it only works so far. So quite often there are different bugs on different systems still, and you have to debug those bugs on different systems in any case, right? So but Java is one of the most popular programming languages, so please don't mock Java too much. It's a great language. Well, maybe it's not a great language, but it's a solid language. And if you think about your C sharp, right? So C sharp was was written like was created a decade after Java, and it was actually able to fix some of the issues that became evident by the decade of Java programming. All right, so yeah, most importantly, you cannot usually fix with any optimization techniques any problems with an algorithm, right? So if you made a dumb choice about the algorithm, then don't try optimization flags or anything like that. It's probably not going to help a lot. It might help a little, but go with a better algorithm. That's a much better advice than trying to squeeze all the performance out of the compiler or JIT, or trying to do some fancy stuff with the JVM flags or anything like that. And by the way, when I said that Java is still slower than in many cases than native code, it is largely due to the effect of garbage collection than anything else. So JIT itself is pretty darn good, believe me, but garbage collection is something that adds a lot of uncertainty, and that renders Java largely, stock Java, standard Java, largely unsuitable for real-time programming, right? So where you need to know exactly the maximum, the maximum latencies of your code execution. But there are extensions to Java that make Java real-time ready, all right, and still have garbage collection. So garbage collection is actually a big thing. So garbage collection is something that we do not have in C and C++. And you all know how you struggle with it, and memory leaks and all that stuff. So Java, C Sharp, and all managed languages largely eliminate this issue. Most of them, the vast majority of them, if not all of them, have garbage collection, and it's a big convenience to programmer. All right, arrays versus pointers. So we've seen this in C, and we've seen how that gets translated into MIPS, right? So with arrays, we need an index, and that index needs to be computed, and computing the index needs to take into account the size of the element. Like if you have an array of integers in MIPS, we know an integer is 32 bits, so you have to increment your index in there, by 4, right? And then we have to add the index multiplied by 4 if it's a word, if it's an integer, to their base address. Okay, so in LW, SW instructions, right? So what you put in the parentheses is this base address, and then this is just the destination, and this is the offset or the displacement. Okay, so the formula is take the value from T0 and add it to the offset, and that would be what we call an effective memory address. All right, so pointers, on the other hand, correspond directly to memory addresses. So when you run this instruction, T1, and then well, right? So we take the address of str and load it into T1. Okay, so T1 is now a pointer because it contains an address in memory. Okay, So both arrays and pointers are useful, and as you can see, they always work together. But you can, in many cases, you can kind of separate them out and implement the same algorithm using either pointers or arrays and indexing. So this is an example. Hopefully, it's pretty straightforward. So let's just keep moving. But please review the differences. Like play this children's game. Note 10 differences. All right, find 10 differences. I don't know if there's 10 or more, but that they are hopefully pretty straightforward. But again, if I'm wrong, let me know. We can go back and I can explain more about that example. All right, so what do we need to remember comparing arrays versus pointers? We need to multiply strength reduced to perform a shift, and we can actually do the actual shift. And with an array version, we require to shift our index so that and make sure that it's inside the loop. And the compiler, of course, if we are talking about a C code, translating C code into their machine code, the compiler can achieve the same effect as the manual use of pointers. So this is actually one of the things that the compiler can optimize for us. It can decide which one is, which approach is more beneficial because it can eliminate induction variables. So fewer variables, fewer registers used is important especially when we have very few registers available to us. Remember, 32 registers in MIPS is not a whole lot. If we think about ARM, then there's even fewer registers in ARM, so 16. Okay, so it's not a whole lot. All right, and now that we mentioned ARM, so here we can give a brief comparison between ARM and MIPS. Both architectures started in 1985, and as you probably know, this textbook that we are using for this class, we're using the MIPS edition. There's also an ARM edition, so both architectures are popular. So there's probably more ARM processors produced than MIPS processors, but ARM is, in a sense, a little more complicated, I think, than MIPS architecture. That's why for the course, I think not to complicate things even more for you, I think MIPS is the right choice. From practical perspective, of course, I think knowing ARM would be a little bit more useful than MIPS, just because there's more software, and it's just my opinion. I could be completely wrong on this, but in my opinion, ARM is more used currently in industry than MIPS. Oh yeah, ARM is used everywhere. So yeah, it's everywhere. Like look at your dishwasher. Look at your washing machine. If they are produced in the last 20 years or so, I'm pretty certain there would be an ARM processor in there, not an x86, not an Intel, but probably an ARM chip. All right, so ARM is an architecture, so it is implemented by many different. So many different vendors have ARM chips, produce ARM chips. All right, because you can just license ARM as an architecture from the ARM company and produce your own chips. All right, so here are some comparisons, and as you can see, so recall we were talking about addressing modes in MIPS, and we discussed there are three of them, like register and indirect, and so there are just three. Well, in MIPS in ARM there are 9, so that would be 3 times more for you to learn. So that is one of the reasons why MIPS and not ARM. Also, there are few registers. Yeah, I said 16, so it's 15, right? So and in MIPS there are 32, but they say 31 because apparently they I guess they do not count probably AT register. That would be my guess. All right. Anyway, well, 031. Maybe that's what they meant. Yeah, maybe I don't know. I'm at a loss, yeah, because I thought ARM had 16 registers and they say 15 and 31, but you know, 0, 31, if you count, it's still 32. All right, so then the notation in this table is probably a little weird, or at least I'm getting confused. Not important, but you can see that with fewer registers, that's the important thing. No matter how you slice it, there are fewer registers in ARM, so writing programs is harder because there are fewer registers. All right, and ARM has some features that are not present in MIPS, and again, say thank you that you didn't have to learn those features. They are actually very convenient, but they add complexity to the ISA, to ARM RSA. So there are there are so-called condition codes that you can put in, that you put in every instruction. So every instruction has those condition codes, and that gives a greater flexibility because basically you can turn each instruction into a conditional. So this is a really cool feature. So if you ever develop any ARM software, in ARM assembly, you're gonna love it, right? So it's very convenient, but of course it makes things a little bit more complicated. Yeah, so I agree. ARM has a higher skill cap, but you can sell that those skills. So there's definitely a market for ARM programming skills, and there's a market for MIPS programming skills as well. But in my observation, it's not as big as the one for ARM. All right. So and here is instruction encoding. So and we compare ARM and MIPS, as you can see, with so the overall structure is roughly the same. So there's a opcode, OP, both in MIPS and ARM. But in ARM, it actually consists of two pieces. There's OPX and OP. And OPX is exactly that prefix that we talked about. Note how this OPX is, we have 4 bytes in all commands, in all instructions. They are prepended by those prefixes, condition codes. Okay, and there are 4, right? So here we have 4, -0 carry overflow, and that's why we need 4 bytes. All right, and yeah, other than that, it just we can see that because there are less bytes, less bits left for things like their jump target, right? 24 versus 26 and MIPS, and that makes programming also a little bit harder, right? You might have more trouble with a long jump than because this jump target has to be, closer. And if we look at other, like this offset is also 4 bytes shorter than this, right? Because again, the same reason we have the additional condition codes that are part of every instruction. One of the things that we were able to save, because there are only 16 registers in ARM, we only need 4. See this 4? We only need 4 bits to encode the register number, whereas in MIPS we need 5 because we have 32 registers. All right, so and then ARM was originally a 32-bit architecture. Then they did a major overhaul when they switched to 64 bits, and so the 64-bit ARM is actually a lot closer to MIPS than their original V7 version 7 of ARM. So and here's just brief list of changes. So let's move on to a brief discussion about Intel x86. So this, if you have a laptop or a desktop, chances are that it is running on the processor with x86 architecture. So this architecture got started with an Intel 8080 processor back in their in 1978, I believe. So it's a pretty old architecture, and this architecture just flourished with IBM PC back in early mid 80s, because that was oh yeah, it's actually here on the slide. 88 is 1974, so 8086 is 1978. Okay, so this architecture actually flourished in mid 80s with IBM personal computers. Okay, so and back then it was clearly their dominant architecture on their PC market, and it is still. I don't really have numbers, available right now, but I I I would dare to say that x86 is still their the dominant architecture. Maybe not as much as it used to be in the 80s, but it is still definitely noticeable. All right, so this is just the development of x86 architecture. You can see it has come a long way from an 8-bit architecture to 16-bit to 24 bits to 32 bits, and every time, every improvement, it was bringing more and more instructions. Why? Because of the compatibility issue, right? Or the curse of the compatibility. So when a new feature had to be introduced, they didn't want to break existing software, and so they would just keep adding things, making sure that all the stuff that used to be in their architecture was still there. And you will see in a few slides what it led to, and it's outrageous. It's just hard to believe what this architecture turned into, and that's why we're not talking about it in much detail, because it is extremely complicated. So I'm sure you would now appreciate your MIPS a lot more, because just 3 addressing modes, 32 registers. The bulk of their registers are general purpose, so they can be used for anything. So they do not have designated uses, right? There are some registers like PC and EIA, but most of the registers are general purpose, and uh, all instructions have the same size, 32 bits. And so it's beautiful if you compare it to an x86 architecture. So x86 is what is known as CISC system, okay? CISC architecture, because it's a complex instruction set architecture, whereas MIPS and ARM are examples of RISC, reduced instruction set computer. And RISC stands for, well, there are very few instructions compared to CISC. Okay, so that you might, to solve a particular problem, to do a particular task, you might need to use 2 or 3 instructions, as we have seen, like multiplying a value in the register and memory is not achievable with 1 instruction in MIPS. It will take more than 1 instruction. In CISC and x86, you can actually do that with a single instruction. But the price you pay for that is there's a lot more different instructions, a lot more to learn, and instructions have different sizes. And in x86, if I remember correctly, the smallest instruction is NOP, which is 1 byte, and the longest instruction is 15 bytes, right? And so different instructions have different sizes, and the size of the instruction is not written inside the instruction in a straightforward manner. So you have to decode several different fields to know how long your instruction is. All right, so it's a mess, by and large. And so, but this architecture is still very, very popular. It's still, I would say, the dominant architecture. So it's no long. It may be, maybe it was elegant back in the late 70s. I would say it was, but it's no longer elegant. It's a huge mess, but it still has a significant market success. Yeah, with AMD, AMD actually came up with EM64T, and then which was an extension of this architecture from 32 bits into 64 bits, and then Intel was trying to resist this, and finally they gave up. But the original technology was called AMD 64. Of course, Intel could not stand anything that would have letters AMD, so they renamed this technology as EM64T, so that it doesn't have the AMD in it. So that and EM64T, that's how Intel calls it now. All right. So as far as their architecture is concerned, so those are basic x86 registers. There's a lot more of them, so this is just a subset. And as you can see, there are just 8 general purpose registers, and their names is A, C, and D are really general purpose. B is usually used for the base address. S is usually used for for stack operations, and yeah, EBP is their base address, EBX is the extended base address, SI and DI are used for indexing, so it's a source index, destination index, and you can see that all those registers have letters E, which stands for extended, because the original registers were 16 bits in the x86 architecture, and they had names without those letters A, C, without those letters E. Okay, so and of course, so all those registers, for compatibility reasons, are still available to you. And then there are segment registers for code, stack, data, and 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 stack. So they are here, and program counter is called instruction pointer in x86. So it's this EIP register, and flags are condition codes, so those are flags like overflow, zero, and things like that. They have their own register E flags here. All right, so what do we have in x86 assembly instructions? Well, we have 2 operands per instruction, and as you can see from this table, there's a great variety. So register and register, this one is the same that we have in MIPS. Register immediate, same, but register memory is something that we didn't have in MIPS, right? So this is one, and vice versa, memory to register, right? So we could actually have a single instruction that would add a register with the contents of the memory, and it would be even able to write it back to the memory. Okay, so and memory immediate is also something that we do not have in MIPS. So those are, kind of instructions that would allow us to use fewer instructions in our code in x86, but actually it's debatable whether our programs would be shorter because those instructions would be longer. Might actually be longer than 4 bytes. All right, so memory addressing modes, we have a greater variety here than we had in MIPS. So we have, this one we had in MIPS, all right, so the base address plus displacement, but we also have scaled versions with, this additional argument scale that multiplies by the value in their index register, and scaled plus displacement. So that's probably one of the most complicated memory addressing modes in x86 architecture. And encoding, as I mentioned, it's all over the place. Here are just a few examples. You see that their length, the size of instructions are different, and yeah, that's not very convenient. But that is in some cases more efficient. All right, so as we have seen, complex instruction sets makes implementation difficult, but in some cases more efficient. So variable number of bytes per instruction, definitely variable number of clock cycles per instruction, and compared to RISC architectures, it's a lot more to learn. So like I said, you should be glad we are not forcing x86 assembly language on you. That would be hard. And to wrap up the conversation in this chapter, a few important things that we talked about. So first, the aspect of the power of the watts that a device consumes, right? Powerful instruction means higher performance, but it also means that if we increase their performance by increasing the clock rate, then it's going to we might hit the power wall. Okay, so remember that. For high performance, we think that writing code ourselves is more efficient. In many cases, it is actually not so. Modern compilers do a much better job with producing very efficient code. But we still need to learn MIPS because we want to look at the underlying architecture. Okay, so that's important for us. That's important for us to learn MIPS. And I know, for many of you, MIPS is already hard. I'm aware of that. Definitely. All right. So yeah, that's the slide that I wanted to show you very much. Note, this is the number of instructions. All right. Look at this number. All right. So if we had to do x86, that's the number of instructions you would have to learn. Compare this to the number of instructions, MIPS instructions, then yeah, it's nothing, right? And yeah, look where it all started with less than 100 instructions, and it grew to over 1,400. That's just crazy. All right, sequential words are not so. Pitfalls or common mistakes that people make related to MIPS. Remember, if you go through an array which is words, increment by 4, not 1. If you go through an array which stores 2 bytes, like your string, with a null terminator, like if it's a 1-character string with a null terminator, increment by 2. Keep pointers to a variable after procedure returns so that it doesn't get overwritten. Okay, and yeah, that concludes our chapter 2, and we will start the Boolean algebra next time. Okay, and yeah, remind me in the beginning of next lecture. I will go over our past calls because there were a few interesting results that I wanted to comment on. All right, it's 1:51, so our time is up. Thank you, folks. Enjoy the rest of your day. Thank you for attending this lecture, and I'm looking forward to see you on Friday. Bye.